So we had started as a review this last time. We have started with again two time period models, then frequencies and n scenarios. Right? This was the notation that we use. So this was notation that we use that we have initial value of n security. All right, so now we have n security right here. That's the initial value L01 to L0n. We have m scenarios, omega 1 to omega n, and we have now each of these n securities having a
we have each of these n securities having you know different values on these m scenarios. So you would really have this matrix here of values of n securities, big N securities in m scenarios. And these are probabilities of each scenarios P1 through Pm, and we're assuming that these probabilities are positive. All right. Okay, again, this is the S matrix. We're calling it S1. And the way it's designed is that if I just multiply this vector with portfolio holdings in each of these n securities, then I get the value of the portfolio in scenario omega 1. And similarly, if I multiply this with portfolio holdings, I get value of the portfolio at omega 2, so on and so forth. Okay, and then we define arbitrage. Basically, any arbitrage is where you make money by taking no risk, and that can be reduced to these settings. So it's a good definition. So it's a strategy, a trading strategy or a portfolio theta such that the initial investment is negative. That means you're getting something upfront. And you lose nothing at time period 1, right? In all the scenarios, your liabilities are 0. Or you can think of initially you're getting either nothing or something, non-negative amount coming to you, non-positive amount you're investing, and you get something non-negative in every scenario, and with some scenario you get something positive for sure, with positive probability, right?
Cost, right? The cost was like S0, like t theta is the cost to us at 0.
S0 theta is the cost to us. No, S0 theta is the investment we make, so it's a cost to us. S1 theta is what we get. It's not the cost to us. It's a reward to us. Yeah, we've just written it that way. Yeah. Okay, we'll use elementary security idea later, but the idea is it's just a security which gives you 1 unit in scenario J, right? It's useful to define these securities.
So in all scenarios, it will give you 0 payoff and one will give you 1.
Yeah. In scenario J, it gives you 1. Hey guys. Okay, then we define the idea of a contingent claim X. And we said it's said to be attainable if there exists a trading strategy theta. So again, this is the investment you make in your N securities, so that at time period 1, you're exactly able to replicate this claim. So it's a replicable claim. It's a, we know how to price it, for example. If we know the value of the initial securities, then we know the portfolio which will exactly replicate it, which we'll know the price of this contingent claim. Yeah?
So the 2-period model.
This is for the 2-period model. I'll just consider 2-period model in this generality, and that's mostly for the interest of time. The ideas will generalize to multiple periods as it is in the binomial setting. So similar mathematics will go through, but we are going to move on to continuous setting soon. So we won't pursue with this, but there's certain inherent, key ideas, linear algebra ideas, which are worth showing in this setting. So that's why I'm focusing on 2-period, but N securities, M scenarios. Okay, so x is equal to s theta. This was the example we saw, just to tell you that one can actually put numbers to these things. All right. The notes are with you now, right? They've been sent.
For lectures 1 and 2, then.
This one here. This,
Yeah, we all upload to them.
you can't just send it right now. If send it
Okay.
just send it immediately, I guess, yeah, so that you can have the lecture notes with you. Okay, we say that a vector of pi which is strictly positive, actually need not be strictly positive, just some entries need to be positive, is a vector of state prices if the t equal to 0 price p of any attainable security x satisfies. So all the attainable securities can be priced as follows. You know, pi k is the price of getting 1 unit in scenario k. So pi k into x w k, x omega k is the value of getting x omega k units in scenario k. And this is the overall price. See, when you're playing with securities, your linearity holds. Price of two securities is the sum of the price of individual securities. So if this is true for attainable claims, then we say pi k is the state price
They
vector,
have to be non-negative.
strictly
Make it
positive.
positive.
Positive, yeah. Positive, non-negative. And one at least has to be positive. Yeah, it can't be zero. Okay, I'm also going to assume existence of a risk-free asset which gives you 1 plus r in every scenario. All I really need to assume is that I have a security which gives a strictly positive payoff in every scenario. But this makes the math simpler, the notation less cumbersome, so I'll just stick to this. For a rupee invested at time 0. Okay. An equivalent martingale measure or risk neutral measure is a set of probability such that the deflated or the discounted prices are martingales. Right? This is clear to you. So S bar 0i is just same as S0i, ith securities price at time 0, because when you discount it, nothing changes. You discount it by a factor 1, this right here. And this has to be equal to the expected value under this neutral probabilities of the pair from the security when discounted by 1 plus r. So that's what we are saying here. And this discounted security we're going to call as S bar I. So what we are really saying is S bar 0i is equal to S bar I in scenario omega j multiplied by probability qj for all scenarios j equal to 1 to n. So you sum them over all scenarios j equal to 1 to m. And this has to be true for all securities I equal to 1 to n.
Time one.
This is time 1, yeah. I'm just not showing the subscript time 1. Okay, so you have prices of security I in time period 1, m values in m scenarios. You discount it by 1 plus r in every scenario. So you get this discounted security prices. Now you take the expectation under probabilities q. And if you have this, this martingale relationship for every security, then you say that these q's correspond to martingale measure. Equivalent martingale measure or risk neutral measure mean the same thing. Right? So everybody with me so far? Any questions? All right, so that was just a definition. So a quick thing to check is that a set of positive state prices exists if and only if the risk neutral measure exists. So there's 1-to-1 equivalence between them, and that's easy to check. So suppose the state price pi exists, then we have this relationship, right? For every security I. And since risk-free security is one of these big N securities, so I'm assuming that, then you have that, for that you have this property, 1 is equal to summation pi k 1 plus r, because risk-free security just gives you 1 plus r in every scenario. And that tells you that the summation pi k is equal to 1 plus r inverse, right? So now I can go back to this equation that I had here and just divide by 1 plus r everywhere. Actually, no, did not divide by 1 plus r at all. Just keep it as it is. The left-hand side is S bar 0i because I've just divided by 1, nothing changes. And the right-hand side, I divide by this, which is 1 upon 1 plus r. and then multiply this quantity by 1 plus r. Right? So it's really just division by 1. You multiply by 1 plus r, you divide by 1 upon 1 plus r. Right? And once I do this, what I get is S bar 0 I is now expected value of the discounted payoff for the ith security, where the probabilities now in this expectation are given by the following quantity right here, which is a non-negative quantity which sums to 1. Right? So the point is, having positive state prices is same as having risk neutral prices, risk neutral probabilities. This is a one-to-one correspondence. The other way around also works. Now suppose one holds. So suppose this equation here holds. Right? I want to just now basically write this equation without the bars. Right? What I can do is I can define my pi k to be qk divided by 1 plus r. Right? So then I'll write this as qk divided by 1 plus r times 1 plus r, and that will get rid of the bar here. So I'm back to this equation right here. So there's one-to-one correspondence. So showing that state prices exist is same as showing that the risk neutral probabilities exist. Again, all this I could have done without assuming risk-free rate, but this just made the calculations look easier, the notation look easier. All right. Now we have our big result. There is no arbitrage if and only if there exists a set of strictly positive state prices. So that's the big result right now that you need to appreciate, that I've defined arbitrage very cleanly, right? Arbitrage exists if a portfolio theta exists with certain desirable properties. So if I say that such a portfolio does not exist, then that would imply that strictly positive state prices will exist, and that will imply that risk neutral probabilities will exist, and vice versa. So that's the big theorem. So just kind of, that's the one you want to take back from this course. It's somewhat non-trivial. In the binomial setting, we got this very cheaply, because no arbitrage implied that there exists, that, the return 1 plus r had to be between u and d. So that made our life much easier. So this is somewhat more sophisticated observation. So again, recall that an arbitrage exists if there exists a portfolio theta such that initial investment is negative, no liability in future, or initial investment is non-negative, right? What you're getting is initial investment is non-positive, so what you're getting is something non-negative, and later on also you get something non-negative, with it being strictly positive with positive probability. So this is how we define arbitrage. So we'll just now make it a clean geometric result. So now consider M to, you go over all theta. So these are all the portfolios that are available to you. And you get a payoff of minus S0 transpose theta. That's what you get, right? And S1 theta is also what you get. So this is what's available to you basically by investing in different portfolios, what is coming to you in both the scenarios, right? And K is just a cone, R plus cross, R plus M. It's just a vector in M plus 1 dimensions of non-negative values, right? Just a vector of non-negative values. And what are we saying? We are saying if there's no arbitrage, then M intersection with K should be empty essentially, except for the zeroth element, right? Theta equal to 0 gives you 0 in M, and K contains the zeroth element. But otherwise, you are saying these two should be empty. There should be no non-negative, non-zero point in K, which also belongs in M. So that would mean there's an arbitrage.
M is considering all the pairs of payoffs possible, like cost and profit possible. And now we're saying K is basically the case where there is arbitrage.
That's right.
Because you had some money
Yeah.
for free.
Yeah.
And what is RM?
Rm plus. This is in mth scenarios, right? S1 theta takes values in m scenarios,
Yeah, okay.
right? Yeah.
Okay, so you can't have positive,
Yeah.
like negative cost and positive.
The only thing that should be common in M and K should be 0. If you have any other point common in them, you have arbitrage. So we made arbitrage into a clean mathematical statement. Is this clear to everybody? Right? Okay, so now that we've got this clean statement, so K is a cone, and cone just means that if I give you a point X which belongs to the cone, then a positive number times X also belongs to the cone. That's the definition of cone, right? So a ray going through it, will stay in the cone basically. It's closed for under rays. And M, by the way, is a subspace. Is this clear to all? So let me just say this again. So K is a cone right here. Let me give you a more dramatic color. No, I think. So K is a cone. That means that if X is in K, then lambda times X is in K for any lambda greater than 0. Right? So that's the definition of a cone. And then we have M is a subspace. What that means for a subspace, if you recall the definition, if X and Y are in M, then alpha times X plus beta times Y are also in M for all alpha and beta, right? In this, you can see this is going to be true. If I give you 2 points, then any linear combination of them is also in that space. All right. And K and M are convex sets. That you can see. If I give you 2 points in those sets, then a line joining them is also in that set. That's what convex set means. Right? So no mystery there. In cone, that's true. 2 points there, line joining them is in the set. In subspace, 2 points there, line joining them is on that set. Now, so this is, I'm just going to take it on faith with you that, from your geometric intuition, that if I give you 2 sets, K and M, which are convex and meet at exactly 1 point, then I can come up with a separating hyperplane that separates them. This requires a proof. Okay. If you really want that proof, then you come to my optimization course at some point. Then we'll do it there.
So the point is that if this is not convex, then they would not meet at all, but many points.
I mean, we can't be sure that there'll be a separating hyperplane. I can construct non-convex sets where there is a separating hyperplane, but I'm not guaranteed it. Here I'm guaranteed. Yeah. Always, no matter what the convex sets are, there'll be a separating hyperplane. And this theorem, separating hyperplane theorem, ensures that there's a in Rm plus 1. What happened? What happened here? Okay, you're with me on this.
Just to show, you want to show that existence of pi implies this. And now we show.
No, now we are saying that there's no arbitrage. So hence,
existence of pi, existence of state prices,
yeah,
imply no arbitrage.
that we'll discuss later. Right now, we're saying existence of no arbitrage implies existence of pi. So existence of no arbitrage means that K and M are disjoint, except for 0.0. Now we're saying that implies existence of pi. That's where we are going right now. Okay, no, it's good to be very clear on this. So K and M don't have anything in common. That's what we assumed. Only 0. So then we are guaranteed by separating hyperplane theorem that there is a in Rm plus 1 such that A transpose X is greater than A transpose Y for all X in K and non-zero and all Y in M. So this requires a proof, but I'm letting you, just take this on faith that such a hyperplane exists. So when you're in K, then you're, on the positive side of the hyperplane, you're, suppose the hyperplane itself was A transpose X plus some constant equal to 0. Then when you're above that, it's positive. When you're below that, it's negative. Okay, so A transpose X for all X in K and non-zero is greater than A transpose Y for all Y in M. So do we accept this? Is that something that we can live with? Okay, so if once we live with that, then you note that, okay, but by the way, our convex sets are not as cleanly separated as we said. Our M is actually a subspace.
I don't know that exists in A such that.
It's like it's a separating hyperplane, right? Separating hyperplane is A transpose X equal to Y. Yeah, one guy is above, one guy is below. It's very clean, huh? This if you go above, A transpose X will become positive. If you go below, A transpose X will become negative.
But then this means the hyperplane is up.
No, A transpose X equal to a constant. That's every hyperplane. Yeah. Right. But it's true. Here I am using the fact that the zero is also involved. So it is, I've gotten away from the constant that way. That's right. Yeah, that's right. So this is, I'm not giving you the details of this. I could, but let that be an offline thing. Then I get this property here. So this you accept. Now you say, okay, A transpose Y is equal to, Y is a subspace. So if Y is a subspace, then what can we say about A transpose Y? Suppose A transpose X is some positive number. Right? For some X, it's a positive number. And then suppose A transpose Y is, let's say, also a positive number. Or let's say it's a negative number. Let's say it's easy that way. Then my subspace also contains minus Y. Suppose A transpose X was 5 for some X. Suppose A transpose 5 is 2. Right? Then no. Suppose A transpose Y is minus 2. Then there's a minus Y, so then A transpose minus Y is equal to 2. And since Y is a subspace, I can multiply Y by a factor of 10 and make it 20. So I'll get a contradiction. I can't have A transpose X less than A transpose Y. The only way I don't get a contradiction is, the only way all of this works out, if what will A transpose Y have to be? It'll have to be equal to 0.
It's non-zero, then you can always.
If it's non-zero, then you can always you can play this game. Yeah.
When you do the separating hyperplane thing, they're assuming that the cone is not inside the subspace, right? They're not in the same.
They're not, yeah, that's what we assume, right? This K and M, they are the cones, they only have one point where they intersect under the no arbitrage condition at 0. Otherwise, they don't intersect. So that's what you're saying. No, so this should be very clear. That under the no arbitrage condition, your K is a cone which is outside of the subspace M. They only meet at point 0. And that guarantees that there's a hyperplane so that A transpose X for all points X in the cone which are not 0 is greater than A transpose Y for all points Y which are in the subspace M. Okay? So now once you accept this, then you can accept that A transpose Y must be 0.
Can you repeat that argument for A transpose Y to be 0?
I mean, suppose it's not 0, because A transpose Y is less than A transpose X, right? I mean, for example, A transpose X, it's not going to be uniformly 0 everywhere. And we've assumed that A transpose X is not uniformly 0 everywhere. So A transpose X is some number. I mean, one can argue that it must be positive because Y has 0 in it. Yeah. Because Y has 0 as an element. So A transpose X must be positive for some X. Now, suppose A transpose Y is positive. No, suppose A transpose Y is negative for some Y. Right?
For the negative alpha.
Then A transpose minus Y is positive. And I can scale Y and I can defeat A transpose X. So the only way this argument will not work is if A transpose Y is equal to 0 for all Y in the subspace. So that condition follows that A transpose Y is equal to 0 for all Y in the subspace. Is this kind of clear? But you can kind of think about it offline and chat with people. Okay, so A transpose Y is equal to 0 for all Y in M. And then A transpose X is greater than 0 for all X in K. X not 0. Right? That follows because A transpose Y is equal to 0. Now, if A transpose X is positive for all X in K, X not equal to 0, is it clear that each AI must be positive?
Yeah. So one guy is negative.
If one guy is negative, then I can take that corresponding x to be positive and the remaining all x's to be 0 and I get a contradiction. Right? Suppose you're saying A1 is negative, then I'll take x1 to be positive and all the remaining x's to be 0. Then my left-hand side here becomes negative, right-hand side I know is 0. So I get a contradiction. So all the A's must be strictly positive. So everybody with me so far on this? Right. Okay, so now what have we said? So, okay, so each AI is positive, that we know. Now let's come back to M. M is what? A1 into minus S0 transpose theta plus these guys A2 plus 1 times S1 theta, and that's equal to 0 for all theta. Right? On the M was a subspace, but basically it was exactly this subspace. Right? So now I can write this as minus S0 transpose, and I've just divided everything by A1. A1 is strictly positive, so I can do this. Right? This transpose into theta is equal to 0. So this is very nice, right? Is how it's all coming together. So when will this be 0 for all theta? When will this quantity here be 0 for all theta?
Left-hand guy is 0.
Only when the left-hand guy. Suppose the left-hand guy is not 0 somewhere.
Just take theta to be that, and
Then you can create a problem, right? Yeah.
just take theta to be the left-hand side.
Just theta to be the guy so that this is not equal to 0. Right? Because it has to be true for all theta. So you then choose a theta in such a manner that left-hand side is not 0, but it has to be equal to 0. So that's a contradiction. So what that means is that this guy here this quantity here has to be equal to 0. If in any unit it's not 0, if any component is not 0, then you can construct a contradiction. You can choose a theta which focuses on that component and gives you a non-zero answer on the left-hand side, but the left-hand side has to be equal to 0, right-hand side. So you get a contradiction. So now what that means is that your S0 is basically equal to S1 transpose pi for some pi which is strictly positive. Right? Because this thing is 0. So S0 transpose is equal to this vector, which is strictly positive, transpose S1. They're equal. That's same as S0 is equal to S1 transpose pi, where pi is strictly positive.
Pi transpose S1.
Well, then that'll be S0 transpose. So now we've just taken transpose on both sides. Yeah. So everybody with us so far? This is kind of like the coolest, simplest part you'll see in this course. You know, after the while, I won't say cool things in a simple manner. Yeah. This M we define here. Yeah, it's a subspace in Rn. Yeah, right here. Well, no, hold on. Let's not. It's in Rn plus 1. See, theta is in Rn, but M is a subspace in. Let's see. I mean, I guess it's just a.
Rn plus 1, right? Because left-hand side guy is a real number. I think that's how
Yeah, it's a subspace in Rn plus 1. Now, right now, I've not claimed that its dimension is M plus 1. That may or may not be true, but it's a subspace in M plus 1, Rn plus 1. Its ambient dimension could be lower. All right. So we have our result. We have one. No arbitrage condition implies existence of this state price vector, and hence existence of equivalent martingale measure. We already saw the equivalence between the state price vector and equivalent martingale measure earlier. So this direction we have. Essentially, this carries on in the continuous time as well. This argument at each time period on each sample path.
Will we see that? How it
Something like this will show up, yeah. I mean, there are caveats there, so I'll show you in some form, but I'll also kind of not go into the gory details of it. But, sorry, not right now. Right now, we can't say the uniqueness of pi. Because, S1 vector could have dependent rows. And then pi may not be unique in that case.
It's full rank then.
Then it's full rank, then you'll get uniqueness. Yeah, that's right. So we'll talk about that later. Okay, and now suppose positive state vector exists, right? So you have S0 is equal to S1 transpose pi. Transpose is clear, right? Because S1, remember, it was all kind of payoff on each omega 1 scenario. So if you go down, it's going to be payoff in different scenarios from security
I said transpose, if you go down, then it's securities now.
in different scenarios.
Different securities, if you take the transpose.
Yeah, no, let's see. So
Each row was an outcome in S1. Now you take the transpose, so now each row is.
yeah, no, I hear you, but let's just, so that for everybody's interest, let me just show the S1 matrix again here. Yeah. So S1 is, if we go, when we look at the transpose, we've kept the security fixed and we've kept the scenarios different, right? So security is fixed and scenario is different. When we multiply by the state prices, we get the value of that security, right?
No, but this is
S transpose, right?
this is S1.
This is S1. So when I take the transpose, then this becomes a row. Yeah, so that's what this becomes a row. And now you multiply this row with state prices. So then you get, okay, what's the price of this state into what you're getting with this security? What's the price of second omega 2, what you're getting from this security? Basically, you get the value of that security. And that should be equal to S0 when discounted. Well, no, with positive state prices, there's no discounting involved. All right, so we get that. Yeah. Okay, so where are we? Right, so now we are saying that suppose a positive state vector pi does exist, right? So we have this existing. So then it's clear that S0 transpose theta is equal to pi transpose S1 theta for every theta. I just multiply both sides with theta, right? I first taken transpose of both of them,
Transpose of both sides.
and then I multiply by theta,
Yeah.
right? Now, what does that mean? If S1 theta is, and pi is strictly positive. Actually, again, I just need maybe, okay, let's assume pi is strictly positive. So then if S1 theta is positive, that will imply that pi transpose S1 theta is positive.
Yeah.
That will imply that S0 transpose theta is strictly positive, right? So you can't have, I mean, S1 theta is strictly positive, meaning S1 theta is positive in some dimension.
Strictly means in each time.
No, so I didn't mean to say strictly. I'm saying, suppose S1 theta is positive in some dimension, then S0 transpose theta is strictly positive.
In one dimension.
Yeah, S0 theta is in one dimension, right? That tells you that you can't have arbitrage of this sort, where you are getting some money up front and having no liability later. Right? Where you were getting non-negative money up front and having non-negative, non-positive liability one time period later. You can't have that. And if S1 theta is 0, if this guy is 0, then S0 transpose theta is equal to 0. So you can't have a situation where you get some money up front and your S1 theta is 0 in all scenarios. So that can't happen either. Right? So no, this implies that arbitrage cannot happen. Arbitrage as we defined it cannot happen because positive state prices exist. Again, same as equivalent martingale measure exists. So we have one-to-one correspondence. ठीक है? Okay, so in summary, assume there exists a risk-free security. The following are equivalent. One is absence of arbitrage. This implies existence of strictly positive state price process. We saw that. And that implies existence of equivalent martingale measure. And existence of equivalent martingale measure implies existence of positive state price process. And that implies absence of arbitrage. Okay, so we have equivalence here of these three things. Okay, so any questions so far online? What's that? No questions. I see. Okay.
One question, right now, we have, like, just if we know arbitrage is true,
Yeah,
we can have multiple state prices and multiple EM.
that's right.
We're not worried about uniqueness.
That's right. That's right. There's one at least state price which is strictly positive and one EMM which is strictly positive.
EMM has to be positive. Probability measure.
There could be EM if state price can be zero somewhere, then EMM can also be zero somewhere.
Oh, you mean strictly positive?
Yeah, for each term. I mean, yeah.
No, but here we're not talking about strictly positive in each.
The absence of arbitrage will imply existence of strictly positive state price
Oh,
process.
yeah, when you get that counted
Yeah.
down, because it's a substance.
But it could be that there are still state price processes where some elements are zero. That could still happen. But there will be one which is strictly
At
positive.
least.
That is guaranteed to you. And existence of strictly positive state price process will guarantee existence of EMM. And existence of EMM, I guess in this case, I should say existence of EMM with all positive, all probabilities positive.
But isn't that?
Because then that would imply, then 3 would imply 2. No, I mean,
The probabilities are always zero ones.
what's that?
Probabilities have to be zero and bad.
Probabilities have to be strictly positive, well, non-negative and lie between 0 and 1. And they should sum to 1. But if you can have positives, if your state price can be 0 for some state,
Strictly positive.
yeah. So, but all I'm saying is if your state price is 0 in some state, then corresponding probability can also be 0 in that state. So it's possible to have that. But right now, what I'm saying here is the theorem here says existence of EMM where all probs are positive. So then it's a completely consistent, it's a correct theorem. All right, any other questions? All right, guys, so we're going to go ahead. So complete markets. So if every random variable X is attainable, yeah. Each entry is strictly positive, yes. That's right. And hence each probability will also be strictly positive. Right. All right. So let's go to complete market. If every random variable X, so if you come up with arbitrary X, X is basically think of X as a payoff from the option. We're looking at M scenarios and you have different options. Now you allow these options to maybe depend upon all the N securities, right? So outperformance option, Asian option, with combining all these securities, some basket options, all those security setting. Or probabilistically, you can think of X as any random variable which takes values in these M scenarios. So if every one of those X can be attained, there's some portfolio theta, so that theta times S1 gives you X, then we say the market is complete. Every X you can conceive of can be obtained by a replicating by this portfolio that you construct. By replicating portfolio, sure. So for all X in Rm, there is this theta in Rn, so that S1 theta is equal to X. Was that? Yeah. So S1 is full rank. And N must be bigger than or equal to small m. Right? N must be equal to small m or bigger than that. And S1 is full rank. But then you can look at these columns as points in the space in m dimensions. And every security can be obtained as a combination of these guys. That's clear, right? That you think of these guys as big N points in M space, M dimension space. Big N is at least as big as small m. And they're full rank. So every point in that space can be a linear combination of these columns. Okay, so geometric intuition is clear. So that's when the market is complete. So now we're going to say, okay, if the market is complete, then what can we say about our kind of, equivalent martingale measure and state prices? So the result is assume that there exists a security with strictly positive price process. But do slow me down. Now, I think what's happening is because all my notes are written I can go much faster. I don't kind of type, so yeah. So that's why I do think I'm covering faster than I. But on the other hand, this way we cover more coursework, so it's probably nothing wrong with that. Okay, assume there exists a security with strictly positive price process, and there's no arbitrage opportunities, right? Then market is complete. So first point is simply risk-free security, which gives you, 1 rupee in the beginning, 1 plus I in every scenario. So suppose that exists.
But for great neutrality, you can have any guy which is always giving you some ball.
That's right. Then you can divide with that rather than dividing by 1 plus R and come up with a different change of measure under which martingales remain. So this is, huh?
You're changing the lowest.
Well, R is deterministic. You can keep it random also. So that's a generality one can do. It's useful. People use it a lot for doing mathematics later on, but we'll worry about that at the right time if we need to. Okay, then the market is complete if and only if there exists exactly one equivalent martingale measure. Right? So the martingale measure also has to be unique in a complete market. So that's somewhat of a non-trivial observation. Trying to see if I can motivate this in a nice manner. Right. I guess maybe one motivation can be think of a world which market is not complete. So we have two securities. 1 plus R, 1 plus R, 1 plus R, and then you have another security S0, S1, 3, S1, 2, S1, 1, right? Now, certain claims are attainable here, those which can be obtained by linear combination of these two securities. And those claims are attainable. So those you can price using a risk neutral measure. So there will be some probability here. You can come up with probabilities P1, P2, P3, so that under the probabilities P1, P2, P3, this security also gives you the rate of return 1 plus R on average, right? But now this P1, P2, P3 is not unique, right? I can move one of them, change the other, and still maintain that rate of return equal to 1 plus R. So it's not unique in that case. So you get uniqueness only when you have complete market. I'm just saying in this case, I can construct P1, P2, P3 so that, S1, 3 into P1 plus S2, S1, 2 into P2 plus S1, 1 into P3 is equal to 1 plus R, right? But then I can have more than one probability of achieving this. Okay, so I don't have uniqueness here. Then things will be different. That's right. So then if the third security is such that, the three securities together cover span the whole space, then you have a complete market. And then then your risk neutral probabilities will be unique. So that's the whole idea. All right. So suppose market is complete. Let's assume that market is complete. So every security can be replicated, right? So in particular, I can have elementary security, which gives me 1 in scenario omega j and 0 everywhere. That can also be replicated. And that's true for every omega j. So every elementary security can be replicated. And hence every x can be replicated. Because it's a basis, yeah. So no, I guess the point was not the point I was trying to make here. So each security can be replicated and it will have a unique price. It can't have two separate prices, right? Then you have arbitrage, you buy low, sell high. It has a unique price. Each security has a unique price, and hence the equivalent martingale measure, which is related to these prices, is also unique.
But
Remember, equivalent martingale measure was just these prices normalized. Yeah.
Like, in for a like, isn't like the way I understand martingale measure is a property, right?
It's a probability measure so that, so let's write that down in this thing. So I'm going to have S0 vector of securities discounted by 1 is equal to summation Qi, let's call it. And then let's, yeah, so this is, okay, let's just go security wise. Then let's call this Qk, k equal to 1 to m S omega k bar I. This has to be true for all I. That is, S bar 0 I is equal to expected value under this change of measure of Si. S bar I. Huh?
Just the measure associated.
Big Q is just the name of the probability measure, so it was small q1, q2 through qm.
It is called the martingale.
Yeah, if this equation is true, so on an average, these S bar process is not changing for each security.
So whichever like probability measure that gives us this probability, that's a
That's the EMF. That's
That's
equivalent
EMF.
martingale measure. Yeah,
and then for uniqueness you mean
yeah.
there's only one probability measure that.
There's only one probability measure. And yeah, I should correct myself. When we say equivalent martingale measure, it is equivalent to original probability measure. So if original probability measure was positive for all the M scenarios, then these Qs have to be positive for all scenarios. So I didn't really need to write that extra sentence I wrote in the theorem earlier. So equivalent martingale measure means that all the components are positive. Okay, so this is, so one could have multiple probabilities which achieve this, right? But when there's a unique one, that's when we are saying EMM is unique.
And just to like by saying we have no arbitrage, we are implying that all of these probability measures are first non-negative. Like sorry, strictly positive.
No arbitrage, what we showed was implies strictly positive state prices exist. And hence, strictly positive, these probabilities exist. Yeah. But you could have in that world, you could still have state prices where some components are 0. And hence, you could have a probability measure, which is still a martingale measure with some probability 0. That could happen.
But that would not be
It still would be no arbitrage, but it will not be complete.
oh okay.
When the markets are complete, yeah, then each elementary security will have positive price, and the probabilities associated with that will also be positive.
Go up to the result you had written.
Uh,
When you're saying suppose market is complete,
mhm.
how does that immediately apply uniqueness of state price, positive state price? Because you assume no arbitrage.
Yeah, we assume you have no arbitrage. So state prices exist,
Yeah.
right?
Yeah.
And each state price, because the market is complete, each state price will have a price, each elementary security will have a unique price, right? So the probabilities have one-to-one matching with this thing, with the state prices.
prices must be unique.
State prices must be unique and hence the probability must be unique.
So we're saying we know state prices exist.
Yeah.
Because the market is complete, it must be unique.
Yeah.
And that then implies EMM is.
That's right. That's right. Exactly.
So, does like more than one state price also imply that there are more than one variable?
Yeah. Because we saw that, once I give you state prices, you normalize them and you get equivalent martingale measure. So if you have more than one, you do this more than one manner. There's one-to-one mapping between state prices and probabilities.
Robert, I didn't get to prove this.
The proof for?
By that you.
So do you agree that the first of all, each elementary security can be priced, right? Because the market is complete. And each elementary security will have a unique positive state price. It can't have two state prices. Because then you have arbitrage, right? So it has unique price.
Okay, and in that.
Because of that, you'll have a unique martingale measure. Because the martingale measure just corresponds to normalizing it. Okay, so now we want to show. Yeah, now suppose unique EMM does exist. So now we're going to assume that EMM is unique. Equivalent martingale measure is unique. And now we'll argue and we'll assume that the market is not complete. And we'll argue that that implies a contradiction. So market must be complete. Okay, everybody with me on this? Okay. So incompleteness implies, so because the market is incomplete, we are assuming that. That means there's a contingent claim X that cannot be attained. That's what incompleteness means. Such a X it does exist, right? So that means there does not exist a theta so that S theta time is equal to X, right? Hence it can't be attained. So S theta is, so for any theta basically. So we are spanning all these columns of S and we're looking at that space. And X does not lie in that space. It lies outside that space. Okay, so that's where again I want you to have a geometric intuition. That means there's some H transpose which is H which is perpendicular to all the columns of S.
So S1.
S1. S1. Yeah, this I can call S1 now, sorry. Right. So then there's a H which is perpendicular to all these columns of S, right? But it's not perpendicular to X. So H transpose X is non-zero. By changing the sign of X, H transpose X is strictly positive. Well, I mean, H transpose X is just a number, right? It's either positive, zero, or negative. It's not zero. Yeah. If it's negative, I just take minus X instead of X.
Oh.
So incompleteness implies that there's a X that cannot be attained.
But isn't that bad?
Yeah, that's by definition. Yeah, that's exactly what we are saying. So that means that there's no theta, so that S1 theta is equal to X,
Yes.
right? So if I look at the space spanned by columns of S, yeah, that does not contain X. So X is outside that. So now I can come up with a H which is perpendicular to S. And that will not be, inner product with X will be non-zero. Because X is lying outside the space. So it requires a little bit of proof. Because I've said X lies outside, that means there is some H which is perpendicular to S, but it's not perpendicular to X.
And what does that give us?
So you agree with that, right?
Yeah.
So let's agree with that right now. That's where we are. And I can, without loss of generality, assume that H transpose X is positive. Because X I can take to be minus X otherwise. Okay. So now I've got H such that H transpose X is positive. I mean, H I can take to be negative. Yeah, not X negative. So H transpose S was 0 and minus H transpose S is also 0. But now that H transpose X becomes positive. So I have this. So I'll use this H to construct a new probability measure, which is also equivalent martingale measure. I'll just perturb my probabilities. So this should have I mean, I could spend more time and think about this and give you a cleaner geometric picture, but let's just live with what we have. So this H is given to you. Now what I'll do is, because I also know that summation Hj is 0. Because H transpose S is 0, there is one S security which gives you 1 plus R in all scenarios. So then H transpose 1 plus R vector 1 is 0. So summation Hj is equal to 0. I know that as well.
There exists one.
See, there's one security which is just giving you 1 plus R in all scenarios. And H transpose that security is also 0.
Because, yeah.
That means summation Hj is equal to 0.
Yeah. Summation of Hj.
Yeah, Hj times 1 plus R.
Oh, and that's a constant.
It's a constant.
So, and now this is a contradiction.
No, not yet. Not yet. This is just telling me that summation Hj is 0.
Think of it this way, it's H transpose S, where S at some instant.
देखो, yeah, no, carry on, but I'll just tell you कि X is X omega 1 through X omega M. It's a payoff you're getting in this scenario, right? Now I've given you H1 through HM transpose, well, it's already transpose. So this times this is equal to strictly positive. Okay? But I've also told you that HM and any security here, S1I omega 1, I guess, S1I omega M is equal to 0 for every security. Right? Such an H is making, it's perpendicular to every security that's there. So in particular, there's a security which gives you 1 plus R in every scenario.
So, you,
That's right. So if this was 1 plus R everywhere, then they'll tell you the summation HI is equal to 0. Summation HI is equal to 0. That's all you can conclude. Right? So we have these conclusions with us that such a H exists, which is perpendicular to every security, but with X, it's not perpendicular. It has a positive component. So now I can construct new probabilities as follows. That's the whole game. I want to construct new probabilities, right? So I've got Hj into 1 plus R here. I don't really need 1 plus R here. But I know that this quantity is true. Summation Hj into 1 plus R is equal to 0. Why is this important? Just by looking at these two equations.
Still maintain the probability
It's still a probability.
for an appropriate lambda.
But I choose yeah. So I mean, it's at least, it's a necessary condition for probability that it still sums to 1. Now to make it strictly positive again, because QWJs were strictly positive, to make it strictly positive, I just choose my lambda very small. Lambda is up to me.
You don't want to make it strictly positive, you want to make it less than 1.
I want all the probabilities to, because it's an equivalent martingale measure, so all the probabilities should still be strictly positive.
But that so if lambda is positive, that is already guaranteed.
Edges are all summing to 0. Some are positive, some are negative. Yeah, some are.
So you
If
need
it was strictly positive, then then this will no longer be a probability. Yeah. So these are good points. All this, so I perturbed my Q in a small neighborhood. So all my Q tildes are still all strictly positive. Okay, so I have a probability here. But the nice, and I'll choose my lambda sufficiently small. Yeah, so that this is true. But now I started off with this equation, right? My original Q was an equivalent martingale measure, right? Just happened to be unique. I assumed it was unique, right? And the market was incomplete. But now I've got this Q tildes here. And the main thing is that when I multiply Hj with Sj and take the dot product, I get 0.
Oh, yes, because.
That's the whole point. This H is perpendicular to all the S's. Right? So that's what's telling me that I can construct a new, that I continued, this relation continues to hold. Right? So I've gone from here to here. And the question is, how was I able to do this? So I could go from here to here because summation Hj Sj j equal to
Shouldn't that be
k,
tilde
should be
also?
k here. Somebody should remind me, that I need to correct these things. This is k here. No, that's not q tilde. I'm bringing q tilde in now. All I'm saying is for q, I had this relationship. Just by adding this, the relationship still continues to be true.
Still.
And that's because summation Sj omega k, and this is hk, I guess. Yeah. K equal to 1 to m, that is equal to 0. Right? Because my h was perpendicular to all the s's.
So in essence, you're not really adding any, because that is perpendicular to.
That's right. So I've given you these new probabilities and I maintain my martingale property under these new probabilities. So I don't have a unique equivalent martingale measure. I have multiple equivalent martingale measures. So whenever there is incompleteness, there are multiple equivalent martingale measures. So whenever you have completeness, you must have unique equivalent martingale measure.
But how is it that Sj,
Mhm.
oh, because it's perpendicular to all securities?
That's right, that's right. That's yeah. Yeah.
But what was the constraint on lambda?
Lambda just had to be small enough so these things are strictly positive each term here. So these are proper probabilities. We know that they sum to 1 because summation Sj is equal to 1. Yeah.
Which scroll up slightly.
Yeah. Yeah. So where do you want me to go, Scroll?
So here, where we use the assumption that the product of H and X is on, strictly positive.
Where have we
All
used?
mean is that H is outside the standard particularity.
We didn't really need to,
We have any equivalence standard.
Right. No, that's right. We never really used it. You're right.
Use for
That H transpose X is greater than 0.
I mean, all we really needed was that such an H should exist, right? And that the summation Hj is equal to 0. Yeah,
What makes it?
that's true. Actually, I made a big deal out of it, but we don't need it. Huh.
What makes it like, if lambda is not small enough, and it's like,
I mean,
it's like not negative, but.
I mean, I'm trying to tell you that, you told me that you had a unique, you're bragging that you had this unique equivalent martingale measure. I'm telling you, no, you have another equivalent martingale measure. So for that, I need all the new probabilities to be different from the old ones and all to be strictly positive.
Why strictly one? Why not?
Equivalent martingale measure means that if the original probabilities are strictly, whenever original probability measure is strictly positive, the new one should also be strictly positive. Whenever the original one is 0, the new one should also be 0. Why we'll see later, but that's how we defined it. That's how we define it, so we're sticking to it. See, because this is all about matching payments in each scenario by scenario. So you want to match it on scenarios which occur with positive probability. If a scenario occurs with 0 probability, what?
The amount of sand that we square.
Amount of sand.
Like,
yeah.
that's.
I mean, you understand my point. If the sand is 0 on a certain scenario, if I've given you a model of stock price, it takes value 100 with positive probability, 50 with positive probability, 0 with positive probability, and 10 million with 0 probability, then 10 million is not so important. It's happening with 0 probability. So you don't want to match the scenario when it's taking value 10 million because it happens with 0 probability. It doesn't happen basically. So now you're saying it doesn't happen. Why make a big deal out of it? Why not just say wherever these are positive, why these are also positive? Because when we go in the continuous setting, this events of positive probability 0 are important because when you combine the sand, it becomes positive. Each sand particle has probability 0. So that's when all this becomes slightly, then one has to be more careful. We take any lambda. I mean, we choose the lambda basically, right? Such a small enough lambda. So Hj exists, that we know, that we got, right? And summation Hj is equal to 0. Now, because Hj exists, we can choose lambda small enough so that this q plus lambda Hj 1 plus r remains positive.
Yeah.
That's all. We can always choose for each j, this has to be true.
You make it arbitrary small.
Yeah. Because it's finitely many, it will always exist. Yeah. If it was infinitely many, you have to worry. Then such a lambda may not exist. Okay, good. Any other questions? That's right. So his point is why is 0? All you need is non-zero. You don't need to be positive. Just such a h should exist, sir. Yeah. Yeah. Yeah.
How is that security gives 1 plus r greater each and each step will exist?
We assume that. That was one of my assumptions in the beginning. Assume there are security with strictly positive price process. So I should correct this because earlier I was presenting this in this generality. But then I said, let me present it simply. Assume there's a risk-free security. So that's all I'm going to assume. But I can extend this to have any security which gives positive payoff in every scenario. Yeah. Yeah, that makes no difference. It's just one security you have like this, you can still have a market which is incomplete. Incompleteness essentially means that your column space is not full ranked. So just having one security which is 1 plus everywhere doesn't really make a difference to that. Okay. But yeah, there's very nice kind of clean intuition that's going on here. And there are nuances one has to be aware of. But yeah, I made our life simpler by assuming 1 plus R everywhere. Otherwise, it becomes, more harder to fathom what's going on. Okay, this should be K. So I think that's it, right? So EMM is not unique, that's a contradiction. And again, if you have a complete market, every option price can be priced. Every option can be priced by a replicating portfolio. So no arbitrage pricing gives you the price of that portfolio. In incomplete markets, there are certain options that cannot be priced, but you can develop bounds on them. So then you have to worry about how to price them. So the risk which is not captured by existing securities, that's residual risk. Then you go back to the economics fundamentals and ask yourself, what does risk really is worth to you? And you use those ideas to price these things. And markets in real world tend to be incomplete. But I don't know how much do traders who actually trade follow this idea and all. Maybe they don't. But yeah. Anyway, that's another topic we should come to at some other point. I don't have great understanding of it right now. Okay, so now we'll move on to some probability stuff. Now basically we'll go back to very basic probability. So this was our kind of initial introduction to key ideas in finance. I showed you them for multiple securities, multiple scenarios in one time period or two time periods, but that would extend to multiple time periods. I just haven't shown it to you. Everything kind of goes right through. But now we'll do everything in continuous time. Okay, so now we'll do basic probability. How many of you have not done a prop stat course here? Because some of you were asking for extension. Okay, so everybody's at least done prop stats course here. So we'll try to go through some of this quickly, but we are doing this in a measured theoretic way. So many of you have not done this in a measured theoretic way, right? So you kind of see that in a fairly quick pace. So some of this, I won't do lots and lots of examples which you would do in a proper analysis course, but I'll assume you'll kind of pick up on your own those things. Okay, the key idea in probability is that of a random experiment, right? That's the whole idea. There's an experiment whose outcome is random, right? That's how we start with probability. And sample space omega collects all possible outcomes of the experiment. So we assume that we can collect all possible outcomes. We can enumerate them. At least we have a clear idea of what they are. That's how we build a theory about this. So rolling a dice, okay, 6 possible outcomes, 1, 2, 3, 4, 5, 6, straightforward. Things become very interesting very quickly. In an experiment of flipping coins infinitely often, infinitely many times. So let omega be the sample space when I'm going to flip a coin infinitely many times. So what's my sample space now? Can you? So H, T, 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 all possible such sequences which are countable in length, right? It's an uncountable space that you know? That's right. So, but it is uncountable, right? You can map it to real numbers. Do you know how to map it to real numbers? Huh? Through the binary expansion, yeah. Through binary expansion, right? You can just kind of, so I don't want to spend too much time on these things, but H can correspond to 1, T can correspond to 0. Look at the interval between 1 and 0 and 1. If your first outcome is 1, you go to the first half, the latter half. If it's 0, you go to the first half. Whichever half you're in, then if the next one is 1, you go to the right side. If the outcome is tails, you go to the left side, and so on and so forth. So every number between 0 and 1 corresponds to a string of outputs, H, T, 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 H, H, so on and so forth. Right? You have to worry a little bit about, okay, some numbers have 2 representations, but let's go away from those things, because if you terminate. What's that?
There's also the matrix that in the.
Sure, sure. Yes, all those things we don't want to cover in this course. All right, so this at least you know. So it's a sample space. The point is already it's not quite clear how to assign probabilities. So if I give you a countable sample space, then you just put sand on every outcome, positive amount, and you know how to assign probabilities to any subset. Probability of any subset is just probability of assigned to every outcome. But now in HTTTTH, this uncountable space, I don't quite know how to assign probability. It's a non-trivial task. Right? Okay, where am I? So yeah. So we need an idea of collection of subsets F of omega, where to each subset probability P can be assigned. Ideally, you want to say that, give me any possible subset, I should be able to assign probabilities to that. Right? But we are going to say that that actually that's not how it works. That's not easy to do. That doesn't work always. Because with probabilities, you want some nice properties. In particular, suppose I want uniform probabilities in outcomes between 0 and 1. I want it to be translation invariant and such things. So all of that breaks down for certain sets. Which we'll cover all this when we do non-measurable sets. I'll just show it to you very quickly. But the point is, it's not possible to assign probability to all possible subsets of a sample space. We'll elaborate on this at the right time. That we can't do. The way we build a theory is, we say, okay, let's collect all the subsets where we can assign probability. And let's restrict ourselves on that. There's no contradiction there at least. Otherwise, you can come up with paradoxes in probability because you've not defined your space, subsets where probability can be defined correctly. All right. So surprisingly not possible to assign probabilities to each and every subset of omega unless you limit yourself to countably many outcomes. A collection of subsets of omega. So now we'll start collecting subsets where we can assign probabilities. That's where we're going with this. So we'll start with an algebra. So everybody knows what an algebra is? It's a collection of subsets which contains, so it's a bag of subsets, right? All the subsets are there. Overall, omega is in this bag. If you happen to find a set A in this bag, then A complement also happens to be in this bag. If there was one A for which A complement was not in this bag, it's no longer algebra. It's disqualified, right? It's a set Chori situation then. Okay. Now if you have A1, A2 through AN are subsets. If you pick up any subsets from this set and you take their union, there should be a set which is the union of these subsets in this collection. So that's what we call an algebra, right? And this is finite collection here, finitely many sets. Now, turns out assigning probabilities to algebras can often be easy. So let's understand that. This is not a big deal. Algebra is a collection, but it's not that many, it doesn't have that many subsets. It doesn't have that many interesting subsets. So you can assign probabilities to it, but what you're doing is not very interesting if you just restrict yourself to that. But let's understand this. So consider again our big sample space omega b, all infinite sequence of heads and tails. Each nu I is either heads or tails. And now consider sets of the following form. You specify nu1, nu2 through nu(n), heads, tails, some n tuple sequence. And now you look at all omegas in your big sample space so that the first n outcomes, first n coordinates match nu1 through nu(n), right? Lots of these guys, right? This AN has a huge collection of omegas in it. Now, how many such AN subsets are there? For fixed n. 2 to the power n, right? I can just vary nu1, nu(n). And 2 to the power n possible subsets formed by combining these subsets. Union, intersection, all these things, So either I take AN nu1 through nu(n) and AN with a different nu tilde 1 to nu tilde n and take their union.
Vary all the nu(n)s.
Vary all the nu(n)s. Pick some of them, keep some of them, don't keep some of them. That way you get total of 2 to the power n subsets.
So you're saying look at AN for nu(n).
Yeah.
Nu(n) is R. Now look at the power set of this.
That's
what.
That's
This is
power
basically
set of this set. Yeah.
power set of the powers.
So power set of AN.
Power set of all these
AN
ANs, yeah.
Just has size 2 to the power, and there's a power set.
There's no power set.
Okay.
Okay, so these are all n outcomes. Yeah, go ahead. N outcomes is a long word, but yeah. Yeah, so let's talk about that for a moment. So first you agree that this power set that we have, right? This power set that we have, that if you see a set in that collection, its complement will also exist. Because any set in this power set is a union of these atoms AN. So yeah, if you have these atoms, then what you don't have are also some atoms, and that's some other set. Right. So let's just let me see. Do I want to do this right now? I can. So think of H H H H H T H T H H T T T H H T H T T T H T T T. These are 8 subsets I get, right, when I look at n equal to 3. Okay, so my omega b has been partitioned into 8 subsets. And now I can look at any combination of these, right, a power set. So include this, and this, I get one set. But then, I've also, because it's a power set, I also have a separate set, which is this. Sorry, not this guy. I mean, the complement is exactly the red is the complement of the, I guess, the violet here.
Yeah, but like, okay, the complement power n, like where n is 3, the complement is this, but it's like I'm taking subsets of 2 to the power n, where I'm choosing n equals to 3, but it can be n can be arbitrarily fixed, so that's what.
But it's fixed. N is fixed.
We fix that to form algebra, right?
Yeah.
So when we're defining the algebra, it's inside, like, whatever we fixed,
So
the
okay.
complement is that.
So let's fix a n. What n do you like? 100 is good enough for you? Okay. So then I get 2 to the power 100 these outcomes, these atoms, H, H, T, 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 H, right? Now I can get subsets by combination of these guys, 2 to the power 100. So if I have a set in that collection, I also have its complement. Okay. If I have some sets in this collection, if I take the union, that's also present. So this will be an algebra. But n is fixed right now. Okay. What's interesting is, so now to go ahead of your point, so what we constructed was Fn, this calligraphic Fn. Now, if I take the union of these collection of power sets for each n, that's also an algebra. Right? Because every set in F3 is also in F4. Right? F3 is just union of 2 sets in F4. And so on and so forth. So if, right, F3 has HHH. That's a union of HHHH and HHHT. They're both in F4. I take the union, I get F, yeah. Union, right?
Union, right?
Okay,
Yeah.
I mean, but this is true for any arbitrary power set,
Yeah.
right?
Um,
I mean, if you take any guy, make a power set out of it, that would be an algebra by definition.
I mean, this has this special structure that F4 is included in F3. So you need that structure, right? It may not always be true.
Okay, so this is.
Yeah.
How F will be contained in F4. If I have an A3,
Yeah.
that would be your set, like, let's say, so we have
some omega 1, omega 2, omega 3, where lots of omega 1, omega 2, omega 3, right?
So which?
And now F4 will have omega 1, omega 2, omega 3, omega 4 in all possible combinations of that.
Would it be right to say that F3 belongs, like, is a subset of F4? Because
It's a subset of F4, yeah. Because F3 is a collection of subsets, F4 is a larger collection of subsets. Every set that's in F3 is already there in F4. Like I said earlier, we have this set here. You have H, this atom is there, H, H, H. Let's have two atoms, T, T, H. These are, this union of these two is a set which is in F3. But now I have in F4 H, 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 T, 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 H, H, T, T, H, T. This is present in my F4. So this set is also present in my F4. So any set you can see in F3 will be in F4. Yeah. Okay, so shall we carry on?
But that's just in this case because TTH and TTHH and TTHT have the same probability as TTH and TTH.
No probabilities, right? What do you mean probability?
Okay, so then take the union of, I don't understand that now that's contained in F3, because then F3 won't even have the sequence of code.
I mean, F3 has sets formed by combining all these atoms.
F4 and all 3-to-1 sequences as well. Four, yeah, but so F3 is contained. Yeah, exactly.
Yeah,
Take
F3 is contained. Yeah. Okay, so this is also an algebra. Now you think it's a big algebra, right? Fn was okay, small, but you take a union of all these Fn's. You think it's a great algebra, but is it? That's a question for you. So we'll answer that in a moment. But first, let me just say one thing. It's easy to assign probabilities to this algebra, to all the subsets in this. So that's a nice property that it has. So if I give you any an, whatever be n, so it's an is an atom, right? Of that n. So I know how to assign probabilities to it. P is the number of new i's which are h, 1 minus p into number of new i's what is. An is corresponding to some omega 1, omega 2 through omega n. It's all the omegas such that the first n coordinates are fixed.
So AN.
It's an atom of
mu is an atom.
An is an atom of Fn.
But AN of mu n is an atom, not AN in general.
That's right. That's yeah, An of nu n is an
Like,
atom.
because just from what we did was we first took AN defined with nu n.
Yeah, so
And
I'm hiding nu n here, but that's true. So nu n's are showing up here.
The reason I'm a bit confused is because first we defined AN.
Yeah.
Then we said there are 2 to the power n nu n. And now you do some trickery and get 2 to the power.
I mean, what we said was An for each nu n is a well-defined set, and we have 2 to the power n such sets.
Because you have 2 to the power n such nu n.
That's right. That's right. That's right. That's what we said.
That's what AN without the nu n mentally would mean.
No, I agree with you. I agree with you. That's it's bad notation. Yeah. Yeah, we do a lot of bad notation every now and then. So this is An nu n. I know his point is valid. This should be P of An nu n. Right? And nu n, I mean the vector here. So that's given by this probability. So I can assign probability to every nu n in that manner. And if I define probabilities in this manner, it's a consistent definition across the whole algebra, this algebra F here. Every set in that algebra will get a probability, and there's no contradiction.
What is this hash guy?
P into number of new i's which are equal to heads, and number of new i's which are equal to tails. Right? Number of heads, number of tails, yeah, on this new head, new outcome. So that's a great point that nu n should be mentioned, yeah. But you agree that we've assigned probabilities to all these guys in a consistent manner. And we have a justifiable reason to feel proud, okay, we've achieved something. No problem so far. I wanted to give you an example, but let me just do that here first, because I've gone into some other direction here.
So why was that not a big algebra?
Yeah, so why is that? So let's answer that here. My notes don't write it properly here. So let's look at the outcome. H, 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 forever. Is this in your algebra? For it to be in your algebra, it has to belong to some Fn, right? For it to be in the union. Does this belong to any Fn? No, it doesn't, right?
But then your n is also going to infinity.
That's okay. That's the whole point. For it to belong to the union, it has to belong to some Fn. Fn can be arbitrarily large, but some Fn should contain it. Some Fn should come up and say, this belongs to me, take ownership.
The F is in some sense countable.
It's countable, yeah.
F is countable, but
And then this is.
Yeah, F has countably many elements. That's true.
this guy is also not.
But it's not there.
It's not.
No, this is uncountable.
This is uncountably many.
This is an element of an uncountable space.
The equivalent of all finite out.
Any outcome in mu b, in omega b, sorry, in omega b is not in Fn. Not a single outcome is there. So it's not that big, right? In some sense, you want to have these outcomes also be present in the collection of sets that you're going to assign probability to. You want to assign probability to this, right? What probability would you like to assign to this? 0, right? Yeah, yeah. So you want at least that technology to be available to you that you can say that this probability is 0. So anyway, so we'll discuss all of this. We will also talk about this very nice algebra on 0-1 space. There's an elegant algebra which we know how to assign probabilities to in a nice manner, but that's not enough. So we need more sets that we can assign probabilities to. So that's why we need sigma algebras. So we'll talk about sigma algebras. We'll talk about, okay, well, we'll just I'll just state a big theorem to you, which says if you can assign probabilities to algebras, it uniquely extends to sigma algebra. I won't prove that theorem. That theorem takes about 4 hours to prove. That's fair comment, right? Cartier-Dory's extension theorem. It's a nice proof. Every PhD student should do it.
What does this say?
It says that any probability measure defined on an algebra uniquely extends to the sigma algebra. Now, what do I mean by sigma algebra? I'll explain in a moment. Yeah, it extends uniquely to all the sets which are.
Sigma algebra just replace the omega with phi. That's it.
No, no, no.
Sigma algebra is not phi to be.
Dekho, I've just told you that phi is an algebra right now.
Sigma algebra definition is A plus A complement S.
Sigma algebra का definition है, if I give you sets A1, A2, A3, countably many sets, then their union is also in the sigma algebra.
This is finite.
Everything is finite right now.
Yeah, we always are not confusing.
So we'll bring it home, I think, here. This point should be brought home clearly.
Finite, finite. You
And-
count it, or just one is finite, one is infinite.
One may have countably many sets, but still the property it has to be an algebra is that if I give you finitely many sets, then their union is also there. And the intersection also. We didn't discuss that, but
We cannot countably many infinite elements, the unit still will be.
that's it. So that's asking for a lot.
And then you can see why sigma me will be, like elements of the algebra will be there.
Each one of those will be there, yes. The whole thing will also be there.
That's why we were so specific about n is finite, right?
That's right. Yeah. But these are real things, huh? There's no way around them. You need to be clean with it. Yeah. All right, guys, I'm going to stop this here. Guys, I'm going to leave now. Any questions so far in the audience? Just let us know what you feel. If I presume that this level of theory is fine for everybody. All right. Bye, everyone.